Dear learner, I welcome you all to the MOOC on Principles of Electrical Sciences. I am Dr. Sanjay Agrawal, Associate Professor in Electrical Engineering, School of Engineering and Technology, IGNOU, New Delhi. So in previous session, we discussed voltage regulation of transformer. We also discussed construction and working of auto transformer. Copper saving in auto transformer was also discussed and derived an expression for this. Dear learner, in this session we would discuss three-phase transformer, its advantages, disadvantages and applications. We would also discuss connection of three-phase transformer. All deficiency and classification of transformer would also be discussed in this session. So first of all, we are going to discuss transformer in three-phase system. So for a proper understanding of this section, you will need to revise your knowledge of balanced three-phase system. In particular, you should know the relation between the line and phase quantities in star connected and delta connected balanced three-phase circuit. You must also know the expressions for the three-phase power and volt ampere. And third thing that you must know, that is equivalence relations between star connected and delta connected balance systems. Now question arises, what is a three-phase transformer? The three-phase system is used to generate, transmit and distribute electrical power. It generates power on a large scale to meet the needs of industries and commercial establishment. Three identical single-phase transformers are connected or combined on a single core to form a three-phase system. Based on the various types of industrial needs, the step-up and step-down transformer are employed for generating, transmission and distributing the electric power. As known, a single-phase transformer is a device that is capable of transferring electrical energy from one circuit to one or more circuit based on the concept of mutual induction. It comprises two coils, a primary and secondary coil, which helps to transform the energy. The primary coil is connected to single phase supply while the secondary is connected to the load. Similarly, a three-phase transformer consists of three primary coils and three secondary coils and is represented as a three-phase system can be constructed using three individual identical single-phase transformer, and such a three-phase transformer is known as bank of three transformer. On the other hand, the three-phase transformer can be built on single core. The winding of transformer can be connected in either delta or star configuration. Now we have to understand three-phase transformer construction. A three-phase transformer is used to transfer a large amount of power. The three-phase transformer is required to step up and step down the voltages at various stages of power system network. The three-phase transformer is constructed in two ways. First, three-phase separate single-phase transformer is suitably connected for three-phase operation, and second way is what? A single three-phase transformer in which the cores and winding for all three phases are merged into single structure. A three-phase transformer generally has three magnetic circuits and that are interlaced to give a uniform distribution of dielectric flux between the high and low voltage windings. The exception to this rule is a three-phase cell type transformer. In the cell type of construction, even though the three cores are together, they are non-interlaced. Here you can see the figure A, which shows the core type three-phase transformer. The three-limb core type three-phase transformer is the most common method of three-phase transformer construction, allowing the phases to the magnetically linked. Flux of each limb uses the other two limbs for its return path, with the three magnetic fluxes in the core generated by the line voltage differing in time phase by 120 degree. Thus, the flux in the core remains nearly sinusoidal, producing a sinusoidal secondary supply voltage. Now, in figure B, you can see cell type three-phase transformer. The cell type 5-limb type 3-phase transformer construction is heavier and more expensive to build than core type 3-phase transformer. 5-limb cores are generally used for very large power transformer as they can be made with reduced height. A cell type transformer core materials, electrical windings, steel enclosure and cooling are much the same as for the larger single phase transformer. The unique arrangement of winding and the core in a 3-phase transformer make it possible to save a great deal of iron by interlinking the magnetic circuit so that the same iron is used by the 3-phase simultaneously. It is interesting to note that 3-phase transformer used for the same purpose requires 1/3 as much iron for the magnetic circuit as a bank of 3 single-phase transformers. Proper flux densities are maintained because of 3-phase currents are displaced 120-degree electrical degree with respect to each other. Now we have to understand what are the advantages of the 3-phase transformer. So first advantage is what? Low cost. A 3-phase transformer is cheaper about 15% than bank of 3 single-phase transformer. It is due to saving in cost of the iron core, of the tank and oil, of the bushing and of the auxiliary apparatus. Second advantage is what? It is very efficient. A 3-phase transformer is slightly more efficient than bank of 3 single-phase transformer. This due to fact that it has shorter magnetic path and consequently the core volume and hence the core loss is smaller. Third advantage is installation and operational cost. Installation and operational cost are also smaller in case of 3-phase units because case of 3-phase transformer there is only one unit to install and operate. Next advantage is less size and floor space required. Since the entire 3-phase assembly is reduced in size and is placed in single tank, additional saving result because the less transformer oil is used, fewer transformer bushing are required and the complete transformer occupies less floor space than bank of 3 single-phase transformer. Next advantage is transportation cost is also low in case of another type. Next advantage is the bank also offers the advantage of derated open delta operation when one single phase unit becomes inoperative. In case of delta connected banks, the faulty unit is simply disconnected and continuity of supply is maintained by operating the bank in open delta at 57.7% of original power capacity till the faulty single phase unit is replaced. Now we have to understand what are the disadvantages of 3-phase transformer. First disadvantage is installation and transportation is difficult. It is larger, heavier than any one single phase transformer and it is more difficult to handle, ship and set in place for operation. In underground application, a bank of single phase units may be preferred on account of ease of transport. Second disadvantage is what? Repair cost is very high. 3-phase transformer are much more difficult and costly to repair than a single phase units. Failure of all unit is the next disadvantage, means in case of breakdown in any coils, the entire unit must be removed from the service rather than just one transformer as in case when single phase transformer are employed. Fourth disadvantage is what? The cost of the spare unit and the cost of the repair is greater with use of 3-phase transformer. Now we are going to discuss the 3-phase transformer connections. The winding of 3-phase transformer may be connected either in star or in delta in same manner as for 3 single phase transformer. Since the secondary may be connected either in star or in delta, regardless of which connection is used on the primaries, there must be 4 ways of connecting of a binding of 3-phase voltages. And what are those connections? It may be the star-star, it may be delta delta, it may be star delta, and it may be delta star. The interconnections are made inside the case so that only the terminal leads need to be brought outside the case. So first of all, we are going to discuss the star-star connection. Here you can see in the diagram also. The star-star connection gives the line voltage root 3 times the phase voltage. It is economical for the small rating, high voltage transformer as the number of turns per phase and amount of insulation required is less. So here you can notice that voltage ratio can be written as VL2 upon VL1, and this VL2 is equal to what? Root 3 times phase voltage of that transformer, and VL1 can be written as root 3 BP1, which is equal to N2 upon N1. Similarly, you can write the current ratio. Current ratio can be written as ratio of IL2 upon IL1, which is equal to IP2 upon IP1 is equal to N2 upon N1, because in case of star connection, line current is equal to phase current. Next connection is a delta-delta connection. Delta-delta connection arrangement is generally used in system which carry large current on low voltage, and especially when continuity of service is to be maintained ever though one of the phase develop fault. So no difficulty is experienced due to unbalancing of the load on secondary side. The conductor required of a smaller cross section as the phase current is 1 upon root 3 times of the line current. So in case of this delta-delta connection, you can write the voltage ratio is equal to BL2 upon VL1 is equal to BP2 upon BP1, because line voltage is equal to phase voltage, which can also be written as equal to N2 upon N1. And if you want to write the ratio of current, that means current ratio can be written as ratio of line current to the line current, that is IL2 upon IL1, and line current in case of delta connection is equal to root 3 times of phase current. So this current ratio can be written as IL2 upon IL1 is equal to root 3 IP2 upon root 3 IP1 is equal to N2 upon N1. Just you have to remember all these formulas. Third connection is star delta connection. So here you can notice in the circuit diagram, such connections are used principally where the voltage is to be stepped down, as for example at the end of the transmission line. The neutral of the primary winding is earth. So voltage ratio can be written as BL2 upon BL1, because the primary side is connected as star connection. So this can be written as voltage ratio is equal to BL2 upon BL1 is equal to BP2 upon root 3 BP1 is equal to 1 upon root 3 N2 upon N1, where this N2 upon N1 is a transformation ratio. Similarly, you can also write current ratio is equal to IL2 upon IL1 is equal to root 3 IP2 upon IP1 is equal to root 3 N1 upon N2. Next connection that we are going to discuss for the three-phase transformer is delta star connection. Again, you can observe in the circuit diagram, such connections are used where it is necessary to step up the voltage, as for example at the beginning of the high tension transmission line. In case neutral point is stable and will not be flowed in case unbalanced loading. So this voltage ratio can be written as ratio of BL2 upon BL1. It can also be written as ratio of root 3 BP2 upon BP1 is equal to root 3 times N2 upon N1. Similarly, you can also write the current ratio is equal to ratio of IL2 upon IL1, and this can also be written as IP2 upon root 3 IP1, which is equal to N1 upon root 3 N2. So the arrangement is very popular in distribution system because it can be used to serve both the three-phase power equipment at the single-phase lighting circuit. The neutral of the secondary is earth to provide three-phase 4-wire system. In such cases, the 11,000/415 volt transformer connection provide a 4-wire secondary with neutral supplying 4th wire. The three-phase equipment is then connected to the line wires to operate at 415 volt, while the lighting equipment is connected between one of the line wire and neutral to operate at 240 volt. Now we are going to discuss the choice between star and delta connection. In star connection with earth neutral, the maximum voltage of the phase winding to ground is 1 upon root 3, or you can say 57.7% of the line voltage. While in delta connection, this is equal to the line voltage in case of earthing of one of the line during a fault. Therefore, the phase voltage, turns and insulation are less in star connection than those in delta connection. And for very high voltage transformer, the star connection on high voltage side is about 10% cheaper than delta connection. A delta connected primary is necessary for a star connected secondary feeding, mixed 3-phase and single phase loads. In case of unbalanced single phase loads on secondary, delta connected primary is necessitated to permit the flow of zero sequence current. So this zero sequence current can be written as I naught is equal to In upon 3, which is equal to 1 upon 3 multiplied by summation of Ia plus Ib plus Ic. So you know, for the balance system, Ia plus Ib plus Ic is equal to 0. This means that only positive and negative sequence currents flows in the lines on delta side. This could also be achieved by the star connected primary, provided the primary and the secondary star points are odd. But this is not recommended because of flow of ground current for unbalanced secondary loads. Now we are going to discuss the all-day efficiency. The efficiency discussed so far is the ordinary or commercial efficiency, which is given by the ratio of output power to the input power. That means this commercial efficiency is equal to output power to the input power. The load on the certain transformer fluctuate throughout the day, as you know. The distribution transformer are energized for the 24 hour, but they deliver very light loads for the major portion of the day. Thus, the iron losses occur for the whole day, but copper losses occur only when the transformer are loaded. Hence, the performance of such transformer cannot be judged by the commercial efficiency only, but it can be judged by the all-day efficiency, also known as operational efficiency or energy efficiency, which is computed on the basis of energy consumed during a period of 24 hours. So, the all-day efficiency is defined as the ratio of output in kilowatt hour to the input in kilowatt hour of the transformer over 24 hours. So if you want to calculate the all-day efficiency, so all-day efficiency can be written as ratio of output in kilowatt hour upon input power in kilowatt hour for the 24 hours. Now we are going to discuss the classification of the transformer. The transformer are classified according to their application. So first transformer that we are going to discuss, that is a power transformers. These transformers are used to step up the voltage at the generating station for transmission purpose and then to step down the voltage at the receiving stations. These transformers are of large capacity, generally above 500 kVA. These transformers usually operate at high voltage load, which would cause continuous capacity copper loss, thus affecting their efficiency. To have minimum losses during 24 hours, such transformers are designed with low copper losses. Second category of the transformer, that is a distribution transformer. These transformers are installed at the distribution substation to step down the voltage. These transformers are continuously energized, causing the iron losses for all the 24 hours. Generally, the load on these transformers fluctuates from low load to full load during this operation. Third type of transformer is instrument transformer. To measure high voltage and current in power system, potential transformer, that is a PT, and current transformer, that is CT, are used respectively. The potential transformer are used to decrease the voltage and current transformer are used to decrease the current up to measurable value. These are also used with the protective devices. Next type of transformer is testing transformer. These transformers are used to step up the voltage to a very high value for carrying out the tests under high voltage. For example, for testing the dielectric strength of the transformer oil. Next type of transformer is special purpose transformer. The special purpose transformer may be designed to serve a special purpose, and these may be used with furnaces, rectifier, welding sets and etc. The next category of the transformer is auto transformer, which has already been discussed. Auto transformer are single winding transformer used to step down the voltage for starting of large three-phase squirrel cage induction motors. Next is isolation transformer. Isolation transformer are used only to isolate electrically the electronic circuit from the main electrical line, and therefore their transformation ratios are usually 1. Category of transformer that we are going to discuss, that is impedance matching transformer. Impedance matching transformer are used at output stage of amplifier for impedance matching to obtain maximum output from the amplifier. So on the basis of three-phase transformer, just I am going to discuss one example. So example is a three-phase 50 Hz transformer has an iron cross section of 400 centimeter square. If the flux density be limited to 1.2 Weber per meter square, then you have to find the number of turns per phase on high and low voltage winding. The voltage ratio is 2200/110 volt. The high voltage side being connected in star and low voltage in mesh. So first of all, you have to notice what are the parameters are given. So here you can say that net cross section of iron, which is denoted by A suffix I, is equal to 400 into 0.9. So when you multiply this 400 into 0.9, it comes 360 centimeter square. Just we are assuming that stacking factor, the ratio of net iron cross section to gross iron section to be 0.9. So by this you can find out the net iron cross section AI, which is coming equal to 360 centimeter square. Now we can find out the peak value of the flux, that is phi max. It can be written as B max multiplied by AI. So value of B max is already given, that is a 1.2, and value of AI you have already calculated, that is 0.036. So just multiply this 1.2 into 0.036, so it comes 0.0432 Weber. So value of peak value of flux is equal to 0.0432 Weber. Now the high voltage side phase voltage can be written as EP1 is equal to 2200 upon root 3. So after the solving it comes nearly 1270 volt. And low voltage side phase voltage EP2 can be written as 110 volt. So turn per phase on low voltage winding, which is denoted by N2, can be written as EP2 upon 4.44 phi max into F. So value of this EP2 is what? It is 110, and 4.44 is a constant term, and phi max you have already calculated, that is 0.0432, and value of frequency is 50. So just put all this value, then you can find out turn per phase on low voltage winding is equal to 11.47, or you can say it is equal to 12. So turn per phase on high voltage winding can also be written as N1 is equal to N2 multiplied by EP1 upon EP2. So value of N2 is what? It is 12, and value of EP1 is equal to what? It is 1270, and value of EP2 is what? It is 110. So after the putting all this value, you can find the turn per phase on high voltage side, that is N1 is equal to 138. So dear learner, in today's session we discussed three-phase transformer, its advantages, disadvantages, and connection of three-phase transformer. We also discussed Alder efficiency and classification of the transformer in this session. Hope you were able to learn all the concept. In the next session we would discuss electrical machine. As you know, there are different electrical machines like DC machines, and this DC machine can be classified as DC motor and DC generator. We would also discuss three-phase induction motor, single-phase induction motor and synchronous motor. So in the next session, first of all, construction and working of principle of DC machine would be discussed in next session. Thank you very much.